Okay, well, thank you very much for the invitation and thanks for tuning in. So, I can only tell from looking at your faces whether you can hear me and whether you can follow what I'm doing. So I usually tell the students to give me a thumbs up if I should move on, or thumbs down if you want me to say more about some subject. Okay. So I'm going to describe a recent result on the inverse spectral problem with Hamid Hazari, who's also tuned in here. And so the result is the well-known problem, can you hear the shape of a drum? So a drum in this talk is a bounded smooth plane domain. It vibrates, I think everybody knows. It vibrates at the frequencies which are the square roots of the eigenvalues of the Dirichlet problem. So I wrote out the Dirichlet boundary problem. That means that the boundary condition is 0, so the drum is tied down at the boundary. And there exists an orthonormal basis of eigenfunctions for this problem. And I wrote down the Laplace spectral map, in part because this talk is highly using the work of Koloshin and Desimoy and Avila, and it's all based on looking at these kind of sequences. So they make a map out of sequences, so I'm writing it the same way. So this is just a sequence of eigenvalues. And Kutz's problem is whether this map is one-to-one from the space of domains to the space of sequences. So up until this time, up until my talk, I guess, the only domain which was proved to be spectrally determined, that is, it's the only domain which has its eigenvalues, was the disk. That was proved by Kutz in 1965 in the paper where he stated the problem. There are domains which are known not to be spectrally determined. There are at least 2 domains with the same Dirichlet eigenvalues, but they're convex polygonal domains. So they're not smooth bounded plane domains in the sense of this talk. And so the general problem of whether you can determine a smooth convex bounded plane domain from its eigenvalues is very much an open problem. And that's the problem that we're all thinking about. So our result is that, this is a result with Hamid Hazari, is that ellipses of small eccentricity are spectrally determined among all smooth plane domains. So this is the first unconditional inverse spectral result since Kutz's result. And it's building heavily on prior work of Avila, Desimoy, and Koloshin on dynamical inverse results. So before I get into the sort of details of what we're doing, I want to review Kutz's proof that a disk is spectrally determined so that you can see a simple model of how an inverse result is proved. So to say that a disk is spectrally determined is to say that if another domain has the same Dirichlet eigenvalues as a disk, then it has to be isometric to a disk. So we don't distinguish domains which are isometric to each other. It translates or rotates. So the way you prove it, the way you prove essentially every inverse spectral result is to form some kind of generating function for the eigenvalues. It's a trace of some function of the Laplacian. Here, Kutz used the heat trace. So he looks at the sums over eigenvalues of e to the minus t times the Dirichlet eigenvalue. Then he looked at the asymptotic expansion of the trace as t goes to 0, and it has singularities at t equals 0. There's a singular term t inverse, whose coefficient is the area. There's a singular term t to the minus 1/2, whose coefficient is the perimeter. And then there are other terms, which aren't in fact actually singular. Well, they wouldn't be on a manifold out boundary. They have 1/2 powers. So in particular, you can determine the area of the domain and the length and the perimeter of the domain from the eigenvalues. And by the isoperimetric inequality, you can determine whether the domain is a disk or not. You know, the isoperimetric inequality says the length squared is greater than or equal to 4 pi area with equality if and only if the domain is a disk. So, okay. These are spectral invariants. These area and perimeter are spectral invariants. And in some sense, we're going to look at more complicated generating functions and try to get more kinds of spectral invariants from them. So, as I say, so we're going to be looking at domains isospectral to an ellipse of eccentricity E. And our result is that if you have the same Dirichlet eigenvalues or Neumann eigenvalues as an ellipse of eccentricity E, then you must be isometric to an ellipse of eccentricity E. So I say it's very different. We're going to use the wave trace rather than the heat trace, but it's based on rather deep new results in billiard dynamics due to Avila, Koloshin, Decimoy. I mentioned also Sorrentino and Way. We're not going to be using their results in our talk, but they're really closely related work with Koloshin. The link between eigenvalues and billiard dynamics is through the wave trace. And
just to be clear, you don't have any genericity assumption, right?
Nope.
Okay.
No assumptions at all.
The domain must be an ellipse. Okay.
No, if you're isospectral to an ellipse.
Right,
we
right.
make no assumption on the competing domains.
Right. But the actual...
no, there's no assumptions on the ellipse either, except that it's small eccentricity.
Right. But it's the object is an ellipse. Got it. Okay.
Right. So, you know, there are there are going to be two different domains. There's omega, the mystery domain, which is supposed to be isospectral to the ellipse, and then there's the ellipse. We make no assumptions about omega. About the ellipse, we just assume that the eccentricity is small. Okay.
You said you assume they're smooth though, right? So no polynomial.
Oh yeah, sure. Yes, we assume we're going to use, well, we use the same number of derivatives as Avila, Koloshin, and Decimoy, which is 39, just because we quote their result and okay. But nobody really tries to optimize.
Tell if there are corners, Steve?
No corners.
No, but can you tell spectrally that
there are a bunch of recent results about determining corners from the wave trace. They have these special diffractive singularities. I think Hamid actually has written some papers about that, and Schur and various other people have written papers on this subject. So yeah, you can tell it has corners. It has very diffractive singularities from the periodic orbits that hit the corners. All right. So I'm going to review a lot of definitions, which a lot of people understand already. What does it mean to play billiards in a domain? It means you start a billiard ball off someplace. I put it on the boundary and you hit it in a certain direction. So the direction means the angle between the tangent line at that point and the ray. The ray hits the boundary and bounces off at equal angles. I call that a Snell polygon condition because it bounces off at equal angles. And then it just keeps on going. So it's a straight line segment. We have a flat metric inside the domain. So it's a straight line in between bounces. Okay. So in dynamics, it's very standard when you're dealing with dynamical systems to try to take a cross section to reduce the dimensionality. So if you think in terms of phase space, which we're going to think of here, then we're looking at geodesic flow or billiard flow in the cotangent bundle of the domain. That's 4 dimensions. We can really restrict it to unitangent vectors with no loss of generality. That's 3 dimensions. But we can cut down one more dimension by only looking at impacts against the boundary. So this is, of course, Birkhoff's original idea, which is, it's called the surface of section. it's completely predictable what the billiard ball does between bounces. So we only need to know what happens at the bounces. So the bounces we can think of as a billiard map, which goes from inward pointing unit tangent vectors to the domain to inward pointing unit tangent vectors. You know, it bounces, you know, when it bounces, the outgoing direction's an inward pointing unit tangent vector. The incoming direction is outward, but we reflect it back inward again. So the billiard map takes the outgoing inward pointing unit tangent vector and then to the reflected, sorry, the incoming one and then to the reflected outgoing one. So that's what this picture says. The billiard map would be taking this incoming one and then to this reflected outgoing one. So, so I just wrote down what I was just saying. You follow an inward pointing unit vector until the next impact where you reflect it inward. And so you're really only looking at the inward pointing vectors, and you can project the inward pointing vectors to the tangent line of the boundary at any point. And you get a unit interval at every point, which I denote by B star of the boundary of omega. So these are the subunit tangent vectors. And so this is an annulus because the boundary is a circle and this is an interval. So sometimes people use this notation, capital pi, for the boundary as a circle topologically. And then you have this interval over here, which represents the ball, the unit subunit vectors at every point through their angles. We use this notation L for the perimeter of the domain throughout the talk. So instead of looking at the whole billiard flow, we just look at the billiard map. We look at a point of arc length S on the boundary. There's an incoming angle, inward pointing angle phi. Then it's going to hit at the first impact at some point at arc length S1. It's all measured from some point, fixed point on the boundary. So you have S1 as the new point in the boundary, and then you have a new reflected angle. So that's the billiard map. And Birkhoff proved that this billiard map is an area preserving diffeomorphism of the annulus. And in fact, for a convex domain, it's what's called a twist map, but I'm not going to probably say much about that unless it comes up in a question. So thumbs up if you're ready to meet. I know this is like just review for most people here. Thumbs up if I should go on. Okay. I can only see a few of you, but anyway, that's thumbs up. So very important notion in billiards is a caustic. So I drew in this picture a convex caustic. So a caustic is a curve lying inside the domain, so that if the billiard ball hits it tangentially on the first, if it hits it tangentially, as in the picture here, like that, it's hitting it tangentially, then every time it bounces off, it continues to hit it tangentially. So caustics correspond to certain things for the billiard map. So the caustic lies inside the domain, which we call physical space or configuration space. The billiard map is a map on phase space, so like cotangent space. So a caustic gives rise to a smooth, closed, and invariant curve of the billiard map. Namely, you just look at the tangent lines to the caustic, and that set of tangent lines, it forms a Lagrangian manifold in the annulus. I mean, in the actual phase space, cotangent bundle of the domain. So caustics correspond to invariant curves. I know a lot of you have seen caustics before, but maybe it's not so familiar that caustics correspond to invariant curves. I'm going to draw you a whole bunch of pictures of this in a moment. Are we okay? All right, I drew a convex caustic, but here's the case of a circle at the top and an ellipse at the bottom. In a circle, the disk is foliated by concentric circles, and all of them are caustics. Less obviously, an ellipse has actually two foliations by caustics. It has confocal ellipses. Those are also caustics. They don't exactly foliate the domain in the technical sense, because as this ellipse kind of squeezes in or becomes narrow or becomes the height squeezes, it'll like collapse onto the line segment between the two foci. So it's a singular foliation, but it's close enough. It's really a foliation by caustics. So these confocal ellipses are called convex caustics because they're convex curves. In addition to that, there are these hyperbolic caustics. So some of the orbits of the billiard trajectory go through the line segment between the foci. And these bounce around, and they have these hyperbolic caustics. The billiard trajectories which lie outside, which don't go through this line segment between the foci, have these elliptic caustics. So let's look at that picture both in phase space and in configuration space. This is the physical space or configuration space picture, and I drew a couple convex caustics, and I drew a couple hyperbolic caustics. If you look in phase space, we're only going to be looking at the convex caustics. Sorry, not quite true. We look at all the different caustics, but the only ones that play a role in my talk are the convex caustics. But in this picture, the separatrix curve, you have it looks like the phase space picture for a pendulum. You have these fixed points here, which these points correspond to the major and minor axis, which are what are called bouncing ball orbits, because you just bounce back and forth. They're period 2, periodic billiard trajectories, bounce back in the major and minor directions. They're period 2 for the billiard map. So that's these things. Well, this is the minor axis, and this one's the major axis. The major axis is a hyperbolic trajectory. The minor axis is an elliptic trajectory. So you get the separatrix curve, and that corresponds to the orbits which go through the foci. If a billiard trajectory goes through a focus, it just keeps going through the focus over and over and over again. So the periodic or the orbits which have convex caustics are the ones outside of the separatrix curve. The one with hyperbolic caustics are the ones inside the separatrix curve. They are extremely different because the ones outside are kind of horizontal. Notice that you have to wrap the picture up. So this point is the same as this point. These are like horizontal, but over here, these are like really circles. They're circles. These horizontal things project diffeomorphically down to the boundary. These over here will have turning points or fault singularities if you try to project them down to the boundary. So they're quite different types of curves. Do you understand what I'm saying? Okay. To date, the only curves that have been used in the inverse problem are these outside ones, sometimes called rotational invariant curves. Birkhoff conjectured that the only billiards which were integrable the only billiard tables with integrable billiards are ellipses. That's one of the most, that's perhaps the most famous conjecture about smooth billiards. And you could think of that in two different ways. One is that
what's his exact notion of integrability here?
Well, there are two different notions of integrability. One is that the physical space is foliated by caustics, and the other, which is more correct, and you know, Birkhoff is a genuine dynamics guy. So this one is that the billiard, the phase space is foliated by invariant curves for the billiard map. Okay, so this is what anybody would this one here is what a dynamicist would call integrable system. This is something rather special about billiard tables. All right. However, Koloshin, for example, uses this definition of integrable, that the convex caustics has a non-empty interior. Okay. Lazutkin proved that for any convex billiard table, there's a KAM positive measure Cantor set of caustics near the boundary. So it's hard to believe caustics even exist in general, but they do. So here's another picture that you can see. So the purple dots correspond to the minor axis, and those are period 2 for the billiard map. The green dots, well, it says here they correspond to a 4-periodic orbit, but a very important thing about the billiard map, which I'll come to in a moment, is that the periodic orbits, of course, they lie on invariant curves, but if you have a periodic orbit on an invariant curve, then every point on the invariant curve is periodic of the same period. That's a very important point. So, Peter, did you hear that? Okay. So the black dots here correspond to the major axis, and so these red dots, the ones outside, as they say, those correspond to the ones with elliptic caustics. And you can find a 3-periodic orbit tangent to a confocal ellipse. Okay, so do you have the picture straight? Everybody got the picture straight?
Just to be clear, this was for this whole discussion's for the integrable ellipse.
This is all for the ellipse.
Yeah.
This is, it
You
says
haven't discussed the problematic general guy. Okay. That's
No.
a spectral guy. Okay.
No, I have to review the ellipse because the reason we're able to hear an ellipse is due to the extremely special geometry and dynamics of an ellipse. Imagine you're isospectral to this. I mean, you have to have a lot of features in common. So now we move on. Now I say something about general convex smooth bounded domains. So when I say convex, every domain in this talk is convex, smooth, and bounded. So a periodic trajectory is a Snell polygon. It's a trajectory which smoothly closes up after hitting off with equal angles some number of times. So the basic invariants, there are certain invariants associated to a periodic orbit. Its length. In the billiard problem, you can associate to it its winding number, so to speak, around the boundary. How many times does the orbit wind around the boundary? And it has a bounce number. How many times does it reflect off the sides? So as we'll see later on, the length is more or less always a spectral invariant, except for some very important cancellation issue, but it's a spectral invariant. But bounce numbers and winding numbers, in general, these are not spectral invariants. We don't know. If you know the length, we have no idea what the bounce number or winding number is. We're going to use the notation gamma PQ for periodic orbits, with winding number P and bounce number Q. And mainly we're going to look at gamma 1Q, orbits that wind around once and bounce off Q times. The rotation number of such a periodic orbit is called P over Q. So rotation numbers were generalized to like all invariant curves. But for periodic orbits, they're just P over Q. So Birkhoff proved there's a reason why 1/2 plays a special role. And in fact, the rotation numbers will go to 1/2 as you tend towards the separatrix curve from outside. They'll go to 0 as you tend towards the boundary from outside the separatrix. He proved that for P over Q, there exists at least 2 distinct periodic orbits with this rotation number. And so the Q, I'm just writing it down in terms of the billiard map. To bounce off Q times means you have period Q for the billiard map. So here are a few examples of periodic orbits for the ellipse. Here's a 3-bounce orbit over here, 3-bounce orbit. And it's caustic. And this is a 4-bounce orbit. You bounce down, you bounce up, you bounce back, you bounce back. So one's a 4-bounce, one's a 3-bounce. This one has hyperbolic caustic, this elliptic caustic. So it was extremely important. The fact that we have this foliation by invariant curves was sort of really due to Poncelet, that periodic orbits for an ellipse come in 1-parameter families. In other words, if you have a periodic orbit on an invariant curve, then every orbit on that invariant curve is periodic also. Okay. So to put it another way, ellipses of highly degenerate billiards. They have highly degenerate, the periodic orbits are degenerate. They come in 1-parameter families. The only ones that don't are the bouncing ball orbits, the major and minor axis. So we're going to be talking about nearly circular domains. Okay, so let's first of all review what happens with the circle. With the circle, a billiard trajectory always bounces off with the same angle at every bounce point. The incoming, outgoing angles are a constant of the motion, and this is the P over Q. That's not true in general, but anyway, that's where this rotation number came from. A 1Q periodic orbit is just a Q-gon, a regular Q-gon inscribed inside the circle. You can calculate its length like this. And of course, you can rotate periodic orbits. So they obviously come in rotate families. Perhaps strange to say, just if you perturb in a disk, you can get all sorts of dynamical behavior to occur. So ellipses are the next simplest types of domains. So here I wrote down the equation of an ellipse of eccentricity E to remind you what the eccentricity is. So these are also completely integrable. We've already mentioned this, that the ellipse itself is foliated by caustics, but a singular leaf, interval through the foci. In the case of a disk, the singular leaf is just the center. So imagine, it's sort of amusing to imagine what happens when you perturb a disk into an ellipse. The center splits apart into 2 foci. So it's sort of amusing to try to figure out like how the dynamical picture for the ellipse grew out of the one for the disk. And we've talked this already. So this is a review. The Birkhoff conjecture is that the only domain with integrable billiards is the ellipse. And they have proved local versions of this.
What is local versions?
Well, I'm going to come to it in a moment because what they actually prove is so much stronger that I'd rather just state it what they actually prove. So there's a definition of a rational caustic. A rational caustic is one for which the orbits are periodic. All the orbits are periodic. So the corresponding invariant curve consists of periodic points. And the rotation number is P over Q, so it's a rational number. That's why they're called rational caustics. This is a definition due to Avila, De Simoy, and Koloshin. A domain is called rationally integrable if the billiard maps has integrable rational caustics of rotation number 1 over q for q greater than or equal to 3. This is just a countable set of curves. Now, they're extremely different from the caustics.
Can you remind us when q gets large?
You're heading towards the boundary.
To the boundary.
You have more and more impacts, right? But you have winding number 1, so you have to be getting closer and closer to the boundary.
So I guess Lazutkin will give you caustics, but not rational caustics.
Precisely.
Okay.
People in KAM, they need Diophantine rotation numbers, and these are rational.
Okay, the opposite. Yeah.
They're the opposite. So this is kind of remarkable because
Sorry to interrupt. I have a question. So these rational caustics with rotation number 1 over q. So they're like normal polygons essentially.
yes.
Right? So
Well,
they bounce just q times and then they close.
that's right.
Okay.
And they're very, very close to being the boundary. We call them creeping rays in PDE. They creep along the boundary. So it's remarkable because Koloshin, De Simoy, and company, they, Avila, they only use these 1 over q rational caustics. Okay. So it's the rationally integrable is way weaker than integrability. You also only need q greater than or equal to 3. You don't need the bouncing ball orbits. So here are the dynamical results. Remember the Birkhoff conjecture. I won't repeat it. Avila, De Simoy, and Koloshin, a rationally integrable billiard table, which is nearly circular. Okay, that's a technical definition, but you can imagine that the curvature function of the boundary has to be sufficiently close to 1. So if it's nearly circular, it must be an ellipse. Later, Koloshin and Sorrentino proved the same result, but when you're close to an ellipse and you're rationally integrable, you have to be an ellipse. So I wrote down that people interested in the inverse spectral problem for Laplace operator immediately like these results because they only have to do with periodic orbits. Periodic orbits are almost the only thing that you can actually identify using eigenvalues. So right away we got excited when they produced these results. See what I'm saying? All the other things use, like we can't really use Lazutkin directly because all we can see with the wave trace is periodic orbits and normal forms. Okay? So this slide is basically a definition of nearly circular. So when we do inverse results, this is kind of a perturbative result. All of these results are sort of perturbative, but not deformation results. We're looking at small perturbations of a circle, but we're not looking at things which have a constant spectrum as epsilon varies. So to do that, we change the domain by sort of making the new domain a graph over the circle, by putting it as the boundary plus epsilon times a normal, times some multiple of the unit normal. So this is a multiple of the unit normal. So that's how you would parameterize a deformation or a small perturbation of a domain. You would just add in epsilon times a little something that pushes it out or in the normal direction. Okay. So there's a nice paper by Ramirez Ross, that's one person, that, so he proved that if the foliation by Caustic persists under perturbations, then it has to be trivial. And he studied Fourier coefficients of the perturbation. He actually has many papers. There's a lot more we can do with this, what he did and has been done. Avila, De Simoy, and Koloshin sort of picked up
What does
from what
trivial mean?
0.
Oh, trivial means 0. Okay.
Trivial in this means isometric. The way I wrote it down is trivial. So they sort of did something similar. They sort of studied the Fourier coefficients of perturbations. They studied data associated to the perturbation, and they studied their Fourier coefficients relative to a very new type of orthonormal basis of functions on the boundary. That was like the brilliance of their paper, was to introduce these functions. So a domain is called delta nearly circular if the perturbation and 39 of its derivatives are less than delta. So now the spectral results are as follows. This is basically all of them. Hazari and I, in 2012, studied the isospectral deformation. That means that the eigenvalues are constant as epsilon changes. And we proved a spectral rigidity result, but we proved it among smooth domains. That was the big advance. We got away from analytic domains and we proved it for smooth domains, but you know, there are two evil things in the subject: analyticity and symmetry. So we got rid of one evil assumption, namely analyticity, and that's the most evil. But we had to assume Z2 cross Z2 symmetry, so that's another evil assumption.
Infinitesimally here mean the same as what was before? Is this a one parameter?
One parameter, and you study the first
and
derivative.
it's constant isospectral
Yes.
on the
That's
deformant.
rigid. Rigid means deformations or trivial.
Okay. So much stronger, a much stronger assumption.
Yes. And Popov and Topalov, they've done quite a lot of work in this field, and they extended the result to ellipsoids. Now, the new result, I'm just stating it again, is that ellipses of small eccentricity are specially determined among all smooth domain. So this has no rigid, it's not a rigidity theorem. The big assumption is small eccentricity, nearly circular. So now let me start getting into the real heart of the proof. So we have to study the length spectrum. First of all, we're going to do wave invariance. The length spectrum is a set of lengths of periodic trajectories. That's a set of numbers in the real line. Without any, if you don't make any assumptions, this could be pretty much any closed set in the real line. You know, you might have a Cantor set, for example. So the length spectrum can be a mess. And we have another notation. If I look at the PQ periodic orbits, with winding number P and bounce number Q, then the lengths of those are denoted by script L gamma PQ. That's a subset of the lengths. That's the lengths of the orbits, which are PQ orbits. And we're mainly concerned with gamma 1Q orbits. Gamma 1Q orbits have been studied since Lazutkin, who is kind of the founder of the whole theory involved here, Birkhoff and Lazutkin. But in particular, was studied by Melrose and Marvisi. So for a gamma 1Q orbit, we don't know what kind of a set that might be, but we look at the inf and the sup, and we write it as little tq and big TQ. I think later on I might write a T1Q and a T1Q. I don't remember, but anyway, little tq and big TQ. And for a nearly circular domain, a very important thing is that the lengths must be less than the perimeter. Because if you're nearly circular and you're not a 1Q orbit, let's say you are a 2Q orbit, you're going to sort of have to go through you're going to have to go sort of more vertical, and you're going to have to bounce. It's like going through two foci, in a ellipse, and it's just going to be too long, and you're going to be higher than the perimeter. That's one of the major ways we use nearly circular. So here's the really basic property, is that the length spectrum has a very strange structure. I'm using notation or terminology from random Schrodinger operators. Don't take that literally. The length spectrum for nearly circular billiards has a band gap structure. So the bands means that, by a band I mean the lengths of 1Q orbits. That's a band. So I mean it's the length spectrum within this interval, little q TQ to big TQ. The gaps are the distances between these intervals. When you change Q, you get a gap. When you have fixed Q, you have a band. That's the notation. So the length spectrum up to the perimeter decomposes for a nearly circular domain entirely into 1Q periodic orbits in their lengths. And these are entirely contained in these bands. And the main point is that the length of a band is, the length of a gap is like Q to the -3. We'll see it on the next slide. And the length of a band is rapidly decaying in Q. These bands are shrinking rapidly. The gaps are also shrinking, but they're not shrinking rapidly. They have to be shrinking because we have to fit them all in between 0 and the perimeter. They have to be shrinking.
And
Yes.
I think you've remarked that no other periodic orbits have lengths in this range, right?
Yes.
That's critical. Okay.
That's critical for many different things, yes. In particular, for no cancellations. So
there was my generic assumption, and you've just explained how you get
yes,
around it, yeah.
yes. So I wrote out a more complicated slide. I don't want to go over this unless you have a question, but we have, see, the band gap structure, we need to actually have quantitative estimates on the sides of the bands and the gaps in terms of the perturbation function f. So we write the boundary as the graph of a function f. We make a one parameter family, the tau is the parameter, but we were just keeping track of how all our estimates depend on f. That's really crucial to get uniform results on band gap structure. So I'm not going to say anything more about this except that there's a difficult theorem there. So I don't really want to talk too much about it. Is it okay?
But it's a purely dynamical result.
This
There's
is
no
purely dynamical.
spectral here.
Yes, purely dynamical. It's okay?
Tau is curvature.
Kappa is curvature.
Kappa is
Tau is
curvature.
just
Tau
tau
is the parameter. Mhm.
tau is a parameter. Yeah.
Kappa is curvature.
Kappa is curvature. All right. Now we get into the wave trace, which a lot of you are experts on. So the wave trace, we take the trace of the wave group, e to the IT square root of Laplacian with Dirichlet boundary conditions. It's a tempered distribution. The only singularities occur when t is 0, or t is the length of a closed orbit. Okay. So here's one of our main theorems. If you have a nearly circular domain, you can hear all of the lengths, up to the perimeter. So you can hear the entire length spectrum up to the perimeter. Roughly speaking, you only have 1Q orbits, so you don't have to worry about PQ orbits interfering in the wave trace with 1Q orbits. And 1Q orbits don't interfere with each other for reasons we'll get to later. but that's another big deal that they don't interfere with each other. So this is kind of review of the wave trace, the Poisson formula. You have singularity expansions for the trace of the wave group, right? You have one for t equals 0, and you have one for every length in the length spectrum. You have these things. So this is called the Poisson formula. At t equals 0, we basically have the same singularities as the heat trace that the Marcotte's used. So, you have an infinite number of these singularities, and you can hear all of them. That's sort of known that you can hear every coefficient of the wave trace at t equals 0 or heat trace. And these are integrals of curvature invariance. Okay, so I think this is more like review for most people. So the first statement we use, the first thing we do is use the singularity at t equal to 0. And we prove that you can actually hear the property of being convex and nearly circular. If you have a domain isospectral to a nearly circular ellipse, with no assumptions at all, you can prove that the domain itself must be convex and nearly circular. So this is a matter of studying the heat trace coefficients. They've been studied extensively by various people. Gilkey, Lance Smith, Melrose, many people have studied these things. So they have a lot of information already about the curvature polynomials you get. They're integrals of curvature polynomials. And you can prove this, that using the wave invariants or these heat kernel invariants, you can show that the curvature of the boundary of your mystery domain, your isospectral domain, differs from the curvature function of an ellipse by something bounded by constant times eccentricity.
So this doesn't use the trace formula, it just uses the heat kernel?
Well, they're essentially the same. It's equals 0.
Yeah, so I'm saying if I
Yes,
didn't...
you could get this from the heat kernel.
Okay.
But anyway...
Kernel asymptotics are the same.
Yes. Yes. So you don't have to make any assumption that your competing domains are nearly circular or convex, because it just follows from the fact that they are isospectral to an ellipse. Now we have to look at singularity. So this is the review, which we can't actually use for this problem, but it's just to review what kind of thing you get in the Poisson formula. So in general, the length spectrum could be a mess. It could be of any closed set. But when you have isolated lengths, and they are lengths of what are called Bott-Morris non-degenerate things, like for an ellipse, then you get nice asymptotic expansions for these things, for these length invariant, these gamma, these are the wave trace invariants at a closed orbit gamma. And that's what it looks like if it's non-degenerate. However, the only two non-degenerate orbits for an ellipse are the major minor axis. And we don't know that our mystery domain has any non-degenerate orbit, so we can't use this. I'm just reminding you what singularities look like if you have a nice situation. Well, we can't use it. We could use this for the ellipse, though. But we don't actually do it this way. We actually use a really nice idea that was, I think, due to Melrose and Marvisi, that you can break up the wave trace into terms corresponding to the number of bounces off the boundary. This is really due to Chazaran. You can write a parametrics for the wave group in terms of number of bounces, but Melrose and Marvisi used it to show that you can decompose the wave trace. So these sigma hat 1 q's, those are the contributions from the periodic orbits with q bounces off the side and winding number 1. In no way, you cannot tell. This is, in general, sigma hat 1q is not a spectral invariant, right? But for nearly circular domains, it is. In general, there's no way you could tell which q you have, or that the winding number is 1 just by looking at the length. But you can do it for nearly circular domains. Because of the band gap property, you can actually figure out where your length is, and you can actually determine the number of bounces just by knowing the length. So, yeah, this is a very good, very nice theorem. These Melrose-Marvisi bounce components are actually spectral invariants for nearly circular domains. By the way, if I might say one thing about this, this is true irregardless of any assumption on isospectrality. So this thing could be used to potentially work on any nearly circular domain. See what I'm saying? We never use the assumption that it's isospectral to an ellipse, or that it is an ellipse, until the very last step. This is a theorem about any nearly circular domain. So I'll let you look at it for about a few more seconds because it's really important. Hey, Peter, did you observe this? Ask a question.
You're talking about the theorem? Yeah, I've heard. I observed the theorem. Yeah.
Okay. Now, this is a really crucial tool. It's a very nice thing of Melrose and Marvisi. It's not stated quite correctly in their paper, but it's stated correctly in our paper. So suppose you have a domain and you want to look at the component, the sigma hat 1q, which is the trace with times restricted to the qth band. Then, using Chazeran's parametrics, q-bounce parametrics, you can actually write down the trace as an oscillatory integral of this extremely special form. It has a very simple, it's only 2 integral signs. This is a homogeneous integral. In a moment, we're going to get rid of one of the integral signs. This is a homogeneous integral in the tau variable. That's this large parameter. It's like 1 over h bar. There's a meaning, there's a geometric meaning of this. So the exponent here is crucial. This is called the loop length function. So at a point S, you have a unique trajectory, which is equal angle law everywhere except at the point S. That's why we call this a loop at S, not a closed orbit at S. So everywhere except at S, this q-bounce orbit has equal angles everywhere else. This is an extremely important function called the loop length function. The critical points of this function occur at the vertices of a periodic orbit with q bounces. So it's really part of a theorem that for these q-fold orbits, you can actually have just one trajectory with q bounces. So Melrose looked at this for q greater than or equal to a number depending on the convex domain. But we're doing this for q greater than or equal to 3. We need all of those. So you can write the trace of the wave group this way, and you have a generating function, the phase function, which is the q bounce loop length function. So this is very geometric. I'll go to the next slide before I explain the geometry, but there's geometry in here.
Just a second, come back. Why do you need it for every Q? I mean, why
Because
is
we need to use Avila and De Simoy and all those. We need to be
and
able
their theorem requires that it's
Q
for
greater
every
equal
Q.
to 3. Yes, you need rational integrability for Q greater equal to 3.
Okay.
So that's very challenging because Melrose and Marvisi only proved that you have this. And in general, the fact that you can write it this way basically means that you're up to that the qth iterative of your billiard map is a twist map, that it takes a vertical to a horizontal. The sort of the graph of the image of the vertical over the point S is horizontal, and you can parameterize that graph by one single phase function on the boundary. That's the symplectic geometry underlying this. That's not how they prove it, by the way. It's just that
They actually probably need all Q in their Fourier coefficient. They are solving some inverse problem somewhere.
they use this sort of variations of the lengths of all the Q bounds gamma 1Q orbits for Q greater equal to 3.
Okay. In other words, we're not proving this rigidity by an asymptotic. I mean, you found this very special set of periodic orbits. You need all of them, and you need the coefficients all to be positive so as to pick up the length. Okay.
Okay, we'll get there in a moment, right? So here's sort of the question that you were asking. The perennial problem in inverse spectral theory is multiplicity in the length spectrum. You could have more than one closed orbit of the same length. They come with, they can possibly, the wave trace invariance of those orbits can possibly cancel each other out. Right? Why? Because you have these I to the sigmas in front of the terms. Sigma is a kind of Morse index or a Maslov index. It's very hard to control sigma and I to the sigma for enough periodic orbits. So it's very hard to prove that you don't get like 1 and I squared occurring, and you cancel out. So it's very important that for 1Q orbits, actually they can never have opposite powers of I to the sigma. You don't get cancellations, and we have 3 different proofs of that now. It's we live and die off of that one. So let me now explain.
Is there a neat reason for this, Steve?
Yes, there are like 2 or 3 good reasons for it. I don't know what would be an easy reason to explain, but can you hold it? Hold it until the end, okay?
Okay.
Yeah, so now what's going to happen? From the fact that you can hear these Q bounce contributions to the wave trace, we have that these 2 things are equal. The Q bounce contribution of the wave trace for your nearly circular mystery domain and that for the ellipse. They have to be equal. Then these Melrose-Marvisi integrals have to be equal for the mystery domain and for the ellipse. Okay, but the ellipse has an extremely special Melrose-Marvisi integral because the loop function is constant. Every single loop is actually a periodic trajectory, and all the periodic trajectories have the same length. So for an ellipse, the Melrose-Marvisi, the loop length function is a constant. No, so we bring it outside the integral, and then the rest of the integral has no oscillation in it. It's what we call a symbol. It's a polyhomogeneous function. It's like a homogeneous function of lambda, like a Laurent series in lambda, with this oscillating factor out in front. But this one over here, it's got an oscillating coefficient. So we proved that if this integral equals this phase has to be constant. If it's constant, it's irrationally integrable. Okay? All right. So, as I say, the critical points are points where there exists a periodic orbit starting at S of type 1Q. In the case of the ellipse, the loop length function is constant. So we proved that if, well, the hypothesis is you're nearly circular and you're isospectral to an ellipse, then your loop length function has exactly one critical value. Hence, it's a constant. Hence, every loop is a closed billiard trajectory. Therefore, it's rationally integrable. You might say that this loop length function is the key dynamical creature we study. The variation of it as you deform a domain is called the Melnikov function. And basically, the whole technique of Kaloshin in all of his papers is to study the Melnikov function. So we kind of did it from a different angle by introducing this mu q, and it's the phase of Melrose-Marvisi. So we kind of combine Melrose-Marvisi and Kaloshin by seeing that the key dynamical ingredient in Kaloshin is the phase function for Melrose-Marvisi. So until the last step, I guess I didn't prepare a slide on like how you prove that. It's sort of like you have to work out the singularity expansion. You have to work it out using distribution law of the phase. So until the last step, where we use that the bands have to collapse. The little big TQ is little tq. If you're isospectral to an ellipse, everything I did holds for every nearly circular domain. The only way we use that it's isospectral to an ellipse as opposed to another domain is that the phase function's constant. If we knew anything about the phase function for any other domain, we could probably prove spectral determination for that. So that's what we're trying to understand now. If we could tell you, if we knew about psi q, I mean the mu q, the loop length function, for any other domain, we could do something with every domain. So there's something very more interesting about the ellipse, which is you have a very special wave trace. And we basically never really used the full, we used it that the phase function's constant for Melrose-Marvisi, but actually you have all sorts of periodic orbits that aren't 1Q, and we never really used them. So if we get to ellipses of large eccentricity, we're going to have to look at other PQ orbits. So, all right, so I think I stopped there.
Well, thank you for a very clear and marvelous lecture and a very beautiful result. If I'm running this, then maybe I'll start by opening it up to questions. Just feel, I don't know how to use chat, so I think just unmute yourself, or maybe Sylvia will.
I think they can unmute themselves.
Yeah. Well, sometimes people prefer to write, or maybe their microphones.
Okay, so why don't you write the chat if you want question, and Sylvia will read it, and otherwise just unmute yourself and ask a question.
Yeah, let me start with Zeb's question, okay? Let me remind myself what the question was. Why do you get no cancellations?
Exactly. Why no cancellation?
Okay. I show you the picture. There are like different ways of understanding this. There's an analytical way and a geometric way to understand it. Look at, this picture is better. We're only looking at these invariant curves out here. The cancellations come, roughly speaking, when you have Morse indices which are not equal to, which are not just plus or minus 1. I mean, when you have different Morse indices, then you get cancellations. Now, what's going on here is that in the phase space, you imagine taking a point on the boundary, wherever it is, and looking at the vertical over that point. Okay? That's the fiber. Now, we're really only looking at this region here. What happens to the vertical in this region? Okay. What's
Okay.
happening to it? Well, everything is just getting stretched out horizontally. It's never turning over.
Okay.
That's the reason. It's only when it turns over you get a Morse index. The times when that vertical turns over, becomes vertical again, it like turns vertical again, that's when you pick up, that's Maslov index, when you get verticals of the Lagrangian manifold.
Okay,
It's
so
never-
you're saying for these essentially Lazutkin curves, but with the rational
Yes,
theory,
yes.
it's really this picture, the same as the picture for the ellipse. You don't get new Maslov indices.
Right, right.
Okay.
Well, I thought you were just asking about the ellipse.
No, no, no. I'm also asking for.
Well, that's more complicated. Why? No, that's more complicated, and it goes back to a theorem of Soga, which says that if you have a degenerate critical point, then actually you can hear it. You cannot cancel out a degenerate critical point. If your mu q function has a degenerate critical point, you cannot cancel. That's his Soga theorem.
Okay.
Like if you vanish more to, if you're not a non-degenerate critical point, you vanish to order 2 or higher, you can actually always hear it. You can't cancel it. It's like these Maslov indices are what happens when you have non-degenerate critical points. They're signatures of Hessians, right?
Yeah.
So you just don't have that formula when it's degenerate. So actually, we only had to worry about the case where you had non-degenerate critical points. And then this picture is basically right. So if you want me to be analytical without this picture, it goes back to the Balian-Bloch formula. You know, you do multiple integrals over the boundary.
Right.
The first contribution, the main contribution comes when you do a q-fold integral over the boundary.
Mhm.
Do only q minus 1 of them and leave the last one. Okay? Then you can apply stationary phase to q minus 1 integral signs. That will produce the Melrose-Marvisi integral. It has a phase in front of it, which comes from 2 sources, but one is that one phase will come from the Morse index. See what I'm saying?
Yeah.
From that, if it's non-degenerate, you get a Morse index, but then that Morse index is very much like this picture.
Okay.
So it turns out that the only phases you can get are e to the I plus or minus I pi over 4. Those pi over 2 things only come about when you have non-degenerate critical points.
Okay. So they can't cancel.
Can't cancel.
Thank you.
Yeah. There is a question in the chat by Vladimir Babkov. He
Okay.
has another nice perturbation of the disk might be a ring with, say, a sufficiently small inner hole. Surely several ingredients you use doesn't seem to work in this case, but maybe there is still some chance to establish the isospectral result?
Good question. I think we'll think about that. You know, the picture changes, but I mean, I'm not sure exactly what the question is, like an annular region between 2 ellipses, I guess, right?
I think it just meant, I mean, I don't know, but like, he's saying that a nice perturbation of the disk is just this, between 2 disks, yeah, he's saying between 2 disks, yeah.
We haven't thought about it like annuli or annular elliptical annuli. We haven't thought about that, no.
About the ellipsoid that you mentioned, somebody
Yeah,
already.
yes, we're working on it. Because there are 3 basic closed trajectories on an ellipsoid. There's a hyperbolic orbit, and there's a sort of a small elliptic orbit and another elliptic orbit if you have a triaxial ellipsoid. When you squash the ellipsoid flat,
You get this.
the hyperbolic orbit becomes the major axis, one of the elliptical orbits becomes the minor axis, and then the third one becomes the boundary.
Mhm.
So we haven't really proceeded that far with it yet, but we're sort of trying to maneuver all this stuff. Usually boundary problems are way harder, but here the boundary helps you because of all these strange reflections off the boundary.
Right. In some way, your method is a bit like Mark Katz's isoperimetric proof that the thing you start off with is somehow extremal, and there are higher dimensional versions of that. But you are now pushing this to these 1Q orbits, and the fact that there's something very special, that phase is constant, seems to be a similar feature. That when you
The problem is, you know, Koloshin and company have not yet generalized their theorem to higher dimensions.
Okay.
So even if we could prove that for the interior of an ellipsoid, billiards in the interior of an ellipsoid, even if we could sort of get, then you have like a really complicated thing. The boundary is two-dimensional. But if somehow we manage to do some analog, we still don't have the punchline of Koloshin theorem.
No, well, I mean, it's quite natural. This is a very, it's a very deep combination of micro-local analysis and dynamics, and everybody has to do their part in order to win. Yeah.
Yes. Well, we're talking a lot with Koloshin, trying to push him to do the things we want him to do.
Okay. Any other questions, comments? Well, if not, then let's unmute everybody and give the speaker an applause. And yeah, thanks a lot. It was great.
Thanks, Steve.
Yeah, I'm gonna be by it.
By the way, Steve, do you know, did Steve vanish?
Pardon me?
Do you know if there's a beautiful theorem of Zegel's that on the disk, the multiplicity is essentially 1. Is there anything like that for an ellipse?
Yeah, in a way there is. There isn't really, but you know, there's explicit formulas for the lengths for an ellipse, but in terms of elliptic functions.
No, I'm talking about the eigenvalue multiplicity.
Yeah. There. So we actually have. Yeah, I don't think anybody knows. I don't think we have some ideas about doing that because of the fact that the eigenvalues are analytic, and you know they're sort of basically simple along the along the circle. So for small perturbations, we think they're simple. Well, we're actually working on it.
This is not known because you're saying you don't know of a result like that, because Zegel's theorem is really a theorem in transcendence theory.
Yeah. I know it's zeros of Bessel functions.
Yeah. No coincidence. Zeros of Bessel function.
Yeah. No, I mean,
we don't know anything like that for an ellipse.
We are definitely thinking about it. In fact, we have another approach to the theorem, the rigidity theorem that we're going to post sometime soon. And that approach uses the eigenfunctions rather than the lengths. And it turned, we were hung up on it because we thought we needed to know the multiplicities for an ellipse, but then actually Luc Hilleret kind of explained that we don't really. Luc Hilleret has been studying that kind of problem a lot, you know, looking at long, thin ellipses and trying to get asymptotics and trying to get simplicity results for at least generic ellipses. So we're almost 100% sure, Hamid and I and Luc Hilleret, for perhaps different reasons, that a generic ellipse has simple spectrum.
Okay.
I mean, due to the symmetries, you have eigenvalues that are exponentially close to each other, but you don't actually have them on top of each other.
Right.
Okay. I'm going to end this meeting. So, I mean, if I leave, everybody.
Okay. Well, thank you.